Imagine a $72,000 bill just suddenly hitting your company's credit card.
Ouch. Yeah.
Right. And now imagine that bill was generated in like exactly 4 minutes. And to make it even worse, it was entirely, undeniably your fault.
That is basically the ultimate nightmare scenario.
It really is. So today we're doing a deep dive into the, frankly, terrifying reality of building infrastructure in the cloud. We've gathered this massive stack of incredibly harrowing source materials for you guys. We're talking actual AWS incident reports, cloud security news, and some painfully honest engineering postmortems.
Honestly, reading through these documents, they read less like technical manuals and way more like, psychological thrillers.
Hopefully.
Like they document the exact precise moments when things just go irreversibly wrong.
Yeah, and so our mission for this deep dive is to basically shortcut your path to being well-informed about all this cloud infrastructure stuff. We're going to analyze 4 real catastrophic mistakes so you can learn how to protect your own projects.
Without having to actually endure the financial and reputational trauma yourself.
Exactly, because
Right.
I think the core issue here is friction. Or actually, no, the total lack of it. Like, if you want to build a physical skyscraper, you need cranes, right? You need
Yeah.
steel, you need hundreds of workers pouring concrete. There is friction everywhere.
Yeah,
But the cloud is basically an accelerator pedal with absolutely no brake pad.
that's a great way to put it. That total lack of friction fundamentally changes the rules of engineering because physical constraints just, well, they simply do not exist here.
Right.
There are no actual hardware servers for you to physically run over and unplug when a system goes haywire. So if you write a loop of code that asks for, say, 10,000 servers, the cloud doesn't pause to ask if you're, really sure about that.
Hey, double check.
No, it just provisions them instantly. So mistakes scale at the speed of light.
Which is terrifying.
Yeah.
And, let's look at how fast that speed of light actually is with our first scenario from the sources. I call this one the 4-minute heist.
Oh, this one is brutal.
It really is. So a developer is just wrapping up their day. They push some code to a public GitHub repository. Totally standard procedure. Except buried inside that code entirely by accident is an AWS access key, which is, really just a simple string of text.
Yeah, but a string of text that basically functions as the digital master key to their entire cloud kingdom.
Right. And if I drop my physical house keys on the sidewalk, I might have, I don't know, a few hours, maybe even a couple of days before someone with bad intentions actually finds them.
If they ever find them.
Exactly. But in the cloud, that timeline is compressed to exactly 4 minutes. Automated scripts find the key. These are malicious bots that literally scan GitHub 24 hours a day, 7 days a week, looking for this specific mistake.
Right.
And within the same 4 minutes, the bots spin up hundreds of massive EC2 instances specifically to mine cryptocurrency. Let's pause right there. Because EC2 instance is one of those technical terms that gets thrown around constantly.
Yeah.
What exactly did those bots fire up?
So, EC2 stands for Elastic Compute Cloud. But in plain English, an EC2 instance is just a virtual server.
Yeah.
You're basically renting a slice of a massive physical computer sitting in an Amazon data center somewhere. And you can rent a tiny one with like the processing power of a flip phone, or you can rent a massive one with the power of a supercomputer.
And I'm guessing the bots don't go for the flip phone option.
Oh, definitely not. These bots are programmed to immediately request the absolute most powerful, expensive ones available because cryptocurrency mining requires just massive computational power to solve those complex math problems.
So they basically just hijack Amazon's supercomputers on your dime.
Precisely. And the underlying mechanism here relies on automated scraping. So these bots aren't humans, casually browsing GitHub repositories with a cup of coffee.
Right.
They tap into real-time data feeds to parse every single line of code uploaded globally the exact millisecond it is published. They use these pattern matching algorithms to look for strings of characters that match the exact mathematical format of an AWS key.
Wow. So it's like accidentally leaving your house keys under the welcome mat. But it's not just a burglar walking by. There's an army of invisible robots simultaneously checking every single welcome mat on Earth every second of every day.
That is exactly it. If you leave the key there, they find it instantly.
And the financial damage here from the report, the bill skyrockets to $72,000 before anyone on the engineering team even realizes what just happened.
Which is just staggering.
And then they frantically call AWS support. Now, according to the postmortems we're reading, AWS might look at the situation and say, you got hacked, we'll refund you. But they also might not. You could just be legally on the hook for a $72,000 crypto mining spree.
And here's the thing, the real vulnerability in this scenario wasn't actually just the leaked key itself.
Wait, really?
Yeah, the catastrophic failure was the permissions attached to that key. And this introduces a really fundamental cloud security concept from the sources, which is IAM least privilege, identity and access management.
Okay, so if I'm building a project, how does least privilege actually, stop the bleeding? Does it limit the budget?
No, it limits the authority. Least privilege dictates that a key only possesses the exact minimal permissions required to do its specific job. So if you have a script that needs to, say, read a single image file from a database, its key should only have the authority to read that one image file.
Nothing else.
Exactly. Absolutely nothing else.
So if the developer had configured this properly, the bots would have grabbed the key, tried to spin up 100 crypto mining servers, and then what happens mechanically?
Mechanically, the AWS system evaluates the requests against the IAM policy attached to the key. It sees the command to launch the servers, checks the key's credentials, and basically just bounces the request back with an access denied error.
Oh, wow.
Yeah, the whole catastrophe only happened because the leaked key had unrestricted administrative level power. The bots basically assume the identity of a super user.
Man, so the real takeaway for anyone building software is that you just have to assume your keys will eventually leak, right? And architect the blast radius accordingly.
Exactly. Assume failure.
But, if external bots are the fast-moving predators of the cloud, what happens when the threat is just our own forgetfulness? Because sometimes the most expensive mistakes are, perfectly quiet and entirely self-inflicted.
Right. Which brings us to the silent killers of cloud budgets.
Yes. This is a painfully relatable scenario from the reports that we're calling the ghost in the machine. So a startup engineer needs to run a quick load test just to see if their application can handle a spike in traffic. They spin up one of those massive, high-powered EC2 instances we just talked about.
The supercomputers.
Right. They run their test, the data looks good, and they log off for the day. And this is the kicker, they go on holiday for 3 weeks.
Oh, no. And the instance just keeps humming along in the background?
Yep. Generating charges by the minute. 24 hours a day, 7 days a week, for 21 days.
It's like leaving your oven on, but the oven costs hundreds of dollars a day.
Exactly. So the engineer comes back from vacation, totally relaxed, tanned, and walks right into a closed-door conversation with their CTO. Because that single forgotten server racked up a $4,200 bill on a project that only had a $500 monthly budget.
That is a rough Monday morning.
It really is. But I have to push back on this because, honestly, it defies basic financial logic. Like, how does a company with a $500 budget even physically allow a $4,200 charge to go through?
What do you mean?
Well, if I try to buy a $4,000 television on a credit card with a $500 limit, the transaction's just rejected at the register.
Yeah.
Why doesn't the AWS system just auto-shut off when the budget is hit?
It's a great question, and it really highlights a fundamental difference in philosophy between a traditional bank and a cloud provider. AWS basically prioritizes availability over financial hand-holding. Yeah, and this gets to the absolute core of cloud elasticity. The entire value proposition of the cloud is infinite scale on demand. If you launch a server, AWS assumes your business absolutely relies on that server staying online to serve your customers.
Even if it's literally bankrupting me.
Well, consider the alternative scenario. Imagine you run an e-commerce site, right? You've set a soft budget of $500. Suddenly, some major influencer posts a video about your product. Traffic spikes 10,000%.
Okay, the dream scenario.
Right. And the cloud does exactly what it is designed to do. It dynamically scales up your resources to handle that massive load. Your bill shoots past $500. Now, if AWS had a hard automatic shutoff right at that limit, your entire business would go dark at the exact moment of your greatest success.
Oh, wow. Yeah.
You would lose tens of thousands of dollars in sales just to save a few $100s on server costs.
Okay, that makes total sense when you put it like that. They don't want to be the ones responsible for pulling the plug on your viral moment. But, there has to be a middle ground between shut my business down and let me accidentally spend a mortgage payment on a forgotten test server.
The middle ground definitely exists, and it's called billing alerts.
Okay.
It sounds incredibly basic, but you would be shocked at how routinely it is ignored by developers when they're spinning up new accounts. You can configure an alert to notify your phone, your email, or your team's Slack channel the exact moment your forecasted spend hits a certain threshold.
Like, say, 50% of the budget.
Exactly. And it doesn't disrupt your infrastructure at all. It just breaks the silence. It taps you on the shoulder long before that $4,200 invoice is permanently generated.
It's essentially an early warning radar for your wallet.
Precisely.
But, while a surprise bill like that requires a highly uncomfortable conversation with your boss, losing money is ultimately a fixable problem. You pay the invoice, you set up the alert, and you move on.
You survive it.
Yeah. Losing customer trust, however, is a totally different nightmare.
Oh, absolutely. Financial wounds heal, but reputational blows can be fatal to a company.
Which brings us to a scenario where the damage goes way beyond just a credit card bill. We called this one the temporary fix that lasted 6 months.
This one is painful to read.
Very. So a company is storing highly sensitive customer data. We're talking names, addresses, maybe even financial records in an AWS S3 bucket. Let's actually demystify that for a second. An S3 bucket, simple storage service, is basically just a giant digital folder in the cloud used to store files, right?
That is probably the most accurate way to visualize it, yeah. It operates as object storage. So unlike an EC2 instance, which gives you computing power to run applications, S3 just holds data. Images, database backups, text files, things like that.
Okay, so this company has this bucket full of sensitive customer data. And during some internal testing, an engineer keeps running into permission errors. Their code simply refuses to read the bucket. Out of pure frustration and facing a really tight deadline, they change the bucket's permissions to public.
Oh, boy.
Yeah, just to bypass the error, just to see if the rest of the code works.
And the psychology of engineering workarounds is a massive factor here. When you are deep in the weeds of complex logic, friction is your absolute worst enemy.
Totally.
A permission error is a massive block of friction. So human nature basically dictates that we find the path of least resistance just to maintain our momentum.
I love the analogy from our source notes on this. They said it's like a bank teller propping open the main 10-ton titanium vault door with a brick just for a second so they can carry some heavy boxes inside without having to spin the combination lock every single time.
It's a perfect analogy. And the critical flaw in that workaround is that human memory is deeply, deeply unreliable. We just forget the brick is there. The engineer finishes their test, logs off for the weekend, and the bucket just stays public.
For 6 months.
6 months.
And the punchline is, it's not an internal security audit that catches this mistake. 6 months later, an external independent security researcher is running automated scans of the internet, and they just stumble upon this wide-open bucket.
And suddenly, it's not just a JIRA ticket anymore.
No, it's a headline. This triggers massive GDPR compliance implications. For anyone listening who's unfamiliar, GDPR is the European privacy law that carries fines up to 4% of a company's global revenue for exposing customer data.
It's ruinous.
Yeah, so there are forced notifications to all their customers saying, hey, sorry, your data was left out in the open. It's just a brutal reputational hit.
Yeah.
But look, AWS has engineers take shortcuts, right?
Yeah.
What is the technical safety net here?
AWS actually introduced a specific blunt force safeguard for this exact human failing. It's a feature called S3 Block Public Access. And what's crucial is that it operates at the overarching account level rather than just the individual bucket level.
So how does that mechanically stop the tired engineer with the brick?
Think of it as a master override switch built into the routing layer of the AWS architecture. If you enable S3 Block Public Access on your entire account, AWS fundamentally alters how it processes incoming requests for your data.
Okay.
So even if an engineer goes into a specific bucket and configures its individual policy to say, allow public read, the overarching account rule intercepts the request. The routing layer says, I see the bucket policy allows this, but the master account switch forbids it.
And it drops it.
Exactly. It drops the request before it ever reaches the actual data.
It literally kicks the brick out of the door.
Yeah.
The engineer can try to prop it open, but the building's architecture just refuses to let the door stay ajar.
That's exactly it. It completely removes the reliance on a human remembering to revert a temporary testing configuration. It enforces the security baseline structurally.
That is brilliant. Okay, so an exposed S3 bucket, as terrifying as it is basically a passive catastrophe.
Yep.
It's just sitting there waiting for someone to stumble upon it. But the real horror movie stuff happens when human error actively hunts down and destroys your infrastructure. Let's talk about the harmless script that took down production.
Oh, man. This is a scenario that genuinely keeps engineering leads awake at night.
Picture an engineer tasked with running a routine cleanup script to delete some old, unused resources. They open their terminal window, they execute the script, but they make one fatal error.
Just one.
They're logged into the wrong AWS account. They run the cleanup script in the live, customer-facing production environment instead of the safe, internal staging environment.
A single keystroke in the wrong terminal window.
And the script does exactly what it was programmed to do. It ruthlessly deletes everything it finds. And in this specific case, there are no backups configured for these resources.
Which is just a compounding disaster.
Right. The result, 4 hours of total global downtime. Emergency war rooms are spun up. The CEO is desperately calling the engineering leads. But honestly, I have to ask a basic question here.
Go for it.
In an era where my laptop has a trash bin I can recover files from, and my word processor has had an undo button since the 1990s, why doesn't a multi-billion-dollar cloud platform have Ctrl-Z for mass deletions?
It's a fair question, but a Ctrl-Z requires a system to retain state. And retaining state requires massive amounts of storage and memory, which creates operational drag.
Wow, right.
The cloud's true power lies in its ability to execute commands instantly, scalably, and without prejudice. When a script interacts with an API endpoint, which, is just the digital doorway where software programs talk to each other, it issues a command.
Okay.
If an automated system needs to delete 1,000 servers to save you money because traffic suddenly dropped, it needs to do it immediately. It cannot pause and put them in a recycling bin waiting for a 30-day human review period.
So it just blindly executes orders. But if we can't have an undo button, how do we prevent the script from torching the wrong house? Like, if I'm an engineer, shouldn't there be an invisible wall stopping me from touching live data while I think I'm in the testing lab?
There absolutely should be, and that is where two critical architectural boundaries come into play from the postmortems: account separation and resource tagging. The script itself wasn't really the failure. The lack of boundaries was the root cause.
Break down account separation for me first.
Okay, so staging and production should never, under any circumstances, live in the same AWS account. Never. Never. They should be entirely distinct environments with completely different login credentials and access roles. If you are logged into the staging account, it should be physically impossible for your terminal to send commands to the production API endpoints. Production is essentially a different universe.
So that stops the wrong terminal window mistake entirely.
Yeah.
What about resource tagging? What does that add?
Tagging adds a really vital behavioral layer of defense. Every single asset in your cloud, every database, every S3 bucket, every EC2 instance should have a metadata label attached to it.
Like a digital sticky note.
Exactly. A tag that explicitly says environment, production, or environment staging. And a well-written cleanup script should be programmed to read that tag before it issues the delete command. The logic is so simple. Check the tag. If the tag says production, the script immediately terminates itself.
Wow. So if production and staging were isolated in separate accounts and the resources were tagged, that script's blast radius would have hit a titanium wall. It would have just been a minor error message on a developer's screen rather than a total company meltdown.
Exactly. It confines the inevitable human error to a safe space.
Okay, let's pull all of this together. We've looked at the leaked GitHub key that invited the crypto miners, the forgotten server that racked up a vacation bill, the public S3 bucket that caused a GDPR nightmare, and the wrong account script that deleted production.
A gallery of nightmares.
Truly. But if we synthesize the mechanisms behind all four of these stories, we arrive at what we should probably call the day one survival kit.
The absolute baseline for operating safely in the cloud.
For everyone listening, if you are working in these environments, these are the non-negotiables. What is the definitive 5-point checklist?
Okay, these are the 5 settings every engineer must enable on day 1 to avoid becoming a cautionary tale. Number 1, billing alerts. Establish an early warning radar to break the silence before a mistake bankrupts your project.
The tap on the shoulder.
Exactly. Number 2, IAM least privilege. Never give an access team more power than it absolutely needs to execute its specific task. Limit your blast radius from the start.
Right.
Number 3, S3, block public access. Apply the master routing override so that human error can't accidentally expose your data to the public internet.
Kick the brick out of the door.
You got it. Number 4, resource tagging. Label every single asset so your automated tools and scripts know exactly what environment they are interacting with. And number 5, account separation. Keep your staging playground and your live customer environment in entirely separate universes with distinct credentials.
You know, what really strikes me about that checklist is that not a single one of those 5 settings requires advanced elite coding skills. You don't need a PhD in computer science to turn on a billing alert or tag a server.
Not at all.
They just require the humility to recognize that humans are incredibly predictably fallible. We get tired, we face tight deadlines, we take shortcuts.
That's the real takeaway here. Designing a secure cloud architecture is less about mastering code and way more about mastering human psychology. You have to engineer your environment with the core assumption that human failure is inevitable.
Well, on that slightly terrifying but highly actionable note, we are going to wrap up this deep dive. Thank you for joining us as we unpack these cloud infrastructure failures. Take 10 minutes today to audit your own environments. Look at your access keys, check your bucket policies, set up that billing alert.
Because the automated bots are definitely checking your welcome mats right now.
They really, really are. But before you go, we want to leave you with one final, lingering thought to ponder based on everything we've covered today.
Yeah, so we've established that human memory and fatigue are the ultimate liabilities in a frictionless, infinite environment. So it really makes you wonder about the future of cloud engineering.
Where's this all heading?
Right. How long will it be until artificial intelligence isn't just helping us write our code, but is actively functioning as a real-time mandatory supervisor? Like, imagine an AI that watches your terminal keystrokes, understands the context of your actions, and physically locks your keyboard the millisecond it calculates you are about to execute a catastrophic mistake.
Oh, wow.
Are we moving toward a future where humans are simply no longer trusted to deploy without a machine holding our hand?
Until next time.